In this section and the next, we're going to talk about two rather special sequences. Here's an example of the first one, and notice that the prevailing characteristic here in generating one term after another is that all we do is add 3. 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10. So what that implies then is that the difference between succeeding terms is 3 for all of the terms. That's the prevailing characteristic for arithmetic sequences, and that's what we're talking about here. Now notice this pattern. A sub 1, the first item in the sequence is 1. To generate the second item in the sequence, one way to think about it is to take the first item and add that common difference, you see? And then for the third item, we can take the second item and add another common difference. And for the fourth item, we can take the third item and add another common difference. Now look at the number of common differences for each of these items. For the second item, we have 1 common difference. For the third item, we have 2 common differences. For the fourth item, we have 3 common differences. Generally, or a little more generally, A sub 1 is the first item in the sequence is A sub 1 plus no common differences. And then A sub 2 is A sub 1 plus 1 common difference. A sub 3 has 2 common differences. A sub 4 has 3 common differences. And then you can generalize it even further to the nth term. You can say, well, the nth term would have, well, let's see, how many common differences? Well, you notice that this number, the number of common differences, is 1 less than the number here. What's 1 less than n? Oh, it's n minus 1. So it's A sub 1 plus n minus 1 times d, common difference. Now, using that kind of model, we can a lot of times generate the expression for the nth term of an arithmetic sequence. And for this arithmetic sequence, it would work like this. We understand that with arithmetic sequences, we have this relationship. That is, the nth term is just the first term plus n minus 1 differences. And now let's plug in the information that we know. For this sequence, A sub 1 is 1. And we have n minus 1 differences, but the common difference we know to be 3. And now just evaluate this expression. And we have 1 plus, let's see, 3 times n, 3n, 3 times negative 1, negative 3. And collecting here, we find A sub n to be 3n minus 2. Now let's see if that's not true. Let me just test it on one of these items in the sequence. We have, let's see, this is the first item, second, third, fourth, fifth. The fifth item is 13. Let's see if replacing n with 5 will give us that item. That is it true that A subscript 5 is 13? Well, we would have 3 times 5 minus 2. That's 15 minus 2, 13. So yeah, this works out well. The general model can be used in problems like this. Anytime we're identifying an arithmetic sequence, we just bring that general model to bear on the problem. And they can have a lot of different looks. This one's pretty straightforward, though. It says find a formula for the nth term of the arithmetic sequence with a common difference of 2 and a first term of 5. So we're given all of the important information. So generating the expression for the nth term works like this. You say, well, the general model for arithmetic sequences is that the nth term is the first term plus n minus 1 differences. All right, then we fill in the information we know. We know that the first term is given as 5, and the common difference is given as 2. And then we just evaluate, we just simplify the expression. We have 5 plus 2n minus 2, and collecting constants on the right, the expression is 2n plus 3. One important aspect of this expression, when we can see a distinct coefficient of the counting mechanism, it turns out that that coefficient of the counting mechanism is the common difference involved in the sequence. Now we're told that the difference is 2 here and we have a 2 here. But if we're not told, if we have an expression, then that coefficient of the counting mechanism will be the common difference. And it kind of makes sense because every time we count here, every time we add another value to n, then we're multiplying that value by 2. You see, 2 times 1, 2 times 2, 2 times 4, 2 times 5. And for successive terms generated by this expression, all we're doing is adding another value of 2 every time we pop in another value for n. Okay, just it's kind of an important thing to notice sometimes in problems like this. Here we're told that we have a common difference of 6, and we're given the value of the second item in the sequence. It's 11. We want to find the 19th item in the sequence. Well, we start with the notion that the nth term is the first term plus n minus 1 differences. And we put in information that we know that's given here. Well, we really need 2 bits of information in order to write the general model. See, the strategy here is to write a general model for the sequence, and then we can find the 19th item in the sequence using that general model. Now, the general model, though, calls for us to have information about a sub 1, which we don't have, and the common difference. Now, we know the common difference is 6. So that much we know, but we need the information about a sub 1. There are really 2 ways that we can find a sub 1. If we know that a sub 2 is 11, you see, and the difference is 6, then let's backtrack. 11 minus 6, you see, would give 5 for that first term. So a sub 1 we know to be 5. But let's take another, a more general kind of approach than just that kind of manipulation. Let's go through and put the information about the second term into the general model and see what happens. You see, it turns out that we can actually find a sub 1 like this. If a sub 2 is 11, then we know that a sub 2 is found by taking a sub 1 and adding n minus 1 differences. But n minus 1, wait a second, n is 2. So n minus 1, you see, would be 2 minus 1, or simply 1 times the common difference, 6. You see, now, a sub 2 we're told is 11. So we have 11 equals a sub 1 plus 6. Subtract 6 on both sides, and we find a sub 1 to be 5 as expected. Now, again, notice what we did. We took the very general model, and we put in information that a sub 2 is equal to 11. A sub 2 is equal to, and then it's a sub 1 plus n minus 1. The n minus 1, it's this 2 minus 1 to give this 1. And then the common difference was given as 6, and then away we go to find the value of a sub 1. We had to make that substitution for 11 here, though, don't forget. Okay, now if a sub 1 is 5, and the common difference is 6, given up above, then the general idea is this. We know that, and you can just start from the very beginning. You can say, well, a sub n is a sub 1 plus n minus 1 differences. So a sub n then, the general idea in this sequence is, let's see, 5 for a sub 1 plus n minus 1 times 6. And then simplify here. So a sub n then is, let's see, 5 plus 6n minus 6. So a sub n turns out to be 6n minus 1. What about a sub 19? That's what we're after. A sub 19 is found by just using this expression, 6 times 19 minus 1. Turns out that this value is 113. Here's another situation. We're told that a sub 4, the fourth item in the sequence, is 20. A sub 13, that is the 13th item in the sequence, is 65. What is the formula for the nth term? Well, once again, we use that general model and just fill in given information. The general model is this. And for a sub 4, you see it's a sub 4 is a sub 1 plus 4 minus 1, or 3 differences. But we're told that a sub 4 is 20. So this is 20 is equal to a sub 1 plus 3 times the common difference. All right, and the information about the other item in the sequence, a sub 13, is 65. So a sub 13 is the first item plus 12 differences, but a sub 13 is 65. Now, notice that we have 2 equations in 2 unknowns, and we can solve this as a system of equations. I'm noticing here that the coefficients on a sub 1 are alike. So I'm going to multiply through in equation 1 by negative 1. And then I'll add to eliminate the a sub 1s. All right, so multiplying here by negative 1, I get all these as negative values. So negative 20 is negative a sub 1 minus 3d. Bring down the other equation and just add them. Collecting here, I get 45. The a sub 1s go out as expected. Minus 3d plus 12d is 9d. Dividing on both sides by 9, I find d to be 5. Now once we find D to be 5, we go back in and back substitute to find the value for A sub 1. If D is 5, then I would have 12 times 5 is 60 here. Subtract 60 on both sides, and I would find A sub 1 to be 5 as well. So A sub 1 is 5, D is 5. And then you go right into the general model and replace with the information about A sub 1 and D. A sub 1 is 5, D is 5. Multiplying here, 5n minus 5, the 5's go out, and we have simply 5n. So the expression, the general expression for the nth term is 5n. Here's a problem involving the sum of items in an arithmetic sequence. Now when we're adding the items in an arithmetic sequence, it's called an arithmetic series, and we actually have a formula to make the calculation. Let's develop the formula. Suppose I have the sum as I runs from 1 to 50 of this expression, items generated by this expression. We know that I has to take on the value 1 and 2 and 3 and 4 all the way up to 50. So we would be adding 50 items here. Now certainly we could generate those separate items and add them, and if we wanted to take that kind of time we could do that, but there is a way to develop a formula here, and I could just show it to you, or we can kind of step through it a little bit, and you might have a tendency to remember it a little more effectively, I believe. Now, because these items differ by the same amount from one another, there's kind of a stair-step effect. If we think about the steps of a stair as having value, that is, if we go up a rung of the stairs, then we're adding value, more value on this rung than the one previously, and so on. And we go all the way up these stairs from A sub 1 to A sub 50. It should make some sense that the middle item in the stairs would be the item which would be the average of all of these. And we can find that sum by taking the average size of one of these items, the average of all of these, times the number of items we have. So the average size of an item times the number of items would give us this entire sum. Now usually to find an average though, we add all the things that we have involved and we divide by the number of things we have. Well, it's the sum of the number of things that we're after here, so we're not going to use that technique to find the average. We can find the average though by doing this. We can take the first item and the last item, add them together and divide by 2. You see, it's the average of the smallest one and largest one times n, because the average of the smallest and largest one is kind of like the one in the middle, which is the average for all of them. Now when I say it's the value of the one in the middle, there isn't always a 1 in the middle. If there are an even number of items here, like 10 let's say, then there is no distinctly middle one. There are 5 that are up here and 5 that are down there, but no distinct middle one. If there are 11, however, then there are 5 at the top, 5 at the bottom, and that 6th item is the one in the middle, you see. So it would be the average size of an item. But here's the way we calculate the average size of the item. It's the first one and last one divided by 2. So it's A sub 1 plus A sub n. I'm doing this generally now. We'll apply it to this specific problem in just a moment. But the average of two things means add them and divide by 2, you see. And so that's the average size of an item. Now a lot of times this expression is manipulated in different ways. It can be used like this, but we're going to use it kind of like this. We're going to write the n over 2 as a fraction and then times A sub 1 plus A sub n. And we're going to designate this as the sum of n items, S subscript n. The sum of n items from an arithmetic sequence is given by this formula. Let's use the formula on this particular problem. Now we need A sub 1 and A sub n, so let's calculate that now. A sub 1, the first item in the sequence, would be, let's see, when I is 1, we have 3 times 1, 3, plus 4, that's 7. So A sub 1 is 7. A sub 50, the last item, you see, is, let's see, 3 times 50, 150, plus 4, 154. So 7 and 154. Let's come over here and use the formula. When we're asked to calculate the sum of n items, you see we write the formula and then fill into the formula. We're adding 50 items here, so n is 50. A sub 1 we said was 7, A sub n 154. Adding here we get 161, 50 over 2 is 25. Multiplying we find the sum of those 50 items to be 4,025. In this one, we want to find the sum of the integers from 1 to 100. From 1 to 100, that means we're taking 1. We're adding 2, then 3, 4, and so on, all the way up to 100. All right, we can use our formula. Now, we know that we have, well, let's see, we have a built-in counting mechanism here. We have 100 items. So this is S sub n. Now, a lot of times when we're subscripting here, sometimes we leave it as S subscript n, or since we're adding 100 items here, we might make this 100 if we want to. That would be appropriate as well. We have 100 over 2 then times, let's see, the first item is 1, the last item is 100. So all of the information is kind of built in. We don't have anything to figure out. We just have to fill in and perform operations. So the sum of the first 100 integers, starting with 1, would be 50 times 101, which turns out to be 5,050. Here's one where we have a little bit of a calculation to make. Find the sum of the first 50 even positive integers. The first 50 even positive integers. Well, that would be, we start with 2, and then the next even positive integer would be 4, and the one after that 6, and then 8, and so on. And we go all the way up, and the 50th one, gee, I don't know what's the 50th one is. What's the value of the 50th one? Well, I'm not sure, but we can figure that out because we have some way of generating the nth term of an arithmetic sequence, remember? So we can use that technique to find that 50th term. Here's what we know right at this moment, though. We know that we start with this idea of our formula, and then the information we know about this is that there are 50 items. So we have 50 over 2. The first item is 2, and it's the last item that we're not sure of at this point. So to find the value of that 50th item, we represent an expression for the nth term. And that expression is found by a sub n is the first term plus n minus 1 differences. Now, we know about the first term and the common difference of 2. So the a sub 1 is 2, the common difference is 2. Evaluating here, we find a sub n to be generated by the expression 2n. So the 50th term is 2 times 50, or 100. So we backtrack over here. A sub n is 100. And away we go. This is 25 times 102, which turns out to be 2,550 for the sum of these 50 items.